Okay, let's start this part of FPGA. And as I said, this FPGA lecture will be very much hardware. Okay, but it's give you an idea that what kind of FPGA resource that you can use. It can help you to efficiently use the FPGA resources. Okay, that's the topics we will cover. Yeah. Okay, this is the modern FPGA architecture. Yeah, this from Xilinx. So inside the FPGA, you have the programmable configurable logic block, and block run, and DSP. Those are the major resources inside the FPGA, and they are very important for computing purpose. Okay, and those components is in a two-dimensional grid, so it's full of the die, and you use a programmable routing to connect them to form all different logic functions. And so besides those computing components, you have a I/O block, and you have the power. Yeah, and they are not on this drawing is not quite correct because actually those I/O block and power connection are scattered around in the chip in the die instead of on the peripheral. Okay, we will introduce later. If it's on the peripheral, it has a lot of bottlenecks. Okay, first let's talk about programmability. Yeah, for the FPGA programmable device, that there are three types of programming technology. One is the Xilinx using the SRAM-based programming technology. Another is flash memory. Another is anti-fuse. And they all have a device available in the market and target in different applications. Yeah. Okay, first let's talk about SRAM-based programming. Yeah. They give you an idea how the SRAM program to form the function. First, let's look at the configurable logic block. And this is a typical LUT. LUT stands for lookup table. Okay. So you use a lookup table to define your functions. As you can see here, so this is a full input LUT. So for full input, you have a total 16 combination. Yeah. So if you draw the truth table, you have the full input I1 to I0. Okay, so you can have a 2 to the 4 combination, and for different combination, then you have output 0, 1. Okay, so the output value is programmed in these SRAM cells. So when you program different value, you can form different functions, logic functions, right? Yeah. And for that's illustrate how to do the programmable interconnect. Okay, so basically you have a SRAM bit to control a switch to determine this connection. For example, if you want to have the AND gate output to this gate input, you have to go through the channels, and those are the wiring. And this wiring is programmable. So you have a SRAM-B1 set to enable this connection. And you set one here, then it goes up here, and then here. Okay, so that's the way to form the programmable connections. Yeah, so this gives you an idea how the SRAM is used to program the function and to program the interconnection. Yeah. And SRAM bit takes up 6 transistors. Okay, actually it's quite costly. Yeah, to use 6 transistor memory cells. So in here, let's look at the SRAM-based programming. The advantage is reprogrammable. Okay, even though when system is running, you can still program your function. Yeah, and Xilinx, I believe Intel Altera also has this function called partial programming. That means inside the FPGA, you have a certain area. Okay, as long as there is isolation, so you have a region. So when this part of a function is running, you can program another region. Okay, they call partial programming. Yeah, partial programming. So with this partial programming, you can actually increase the resource of the FPGA. You can increase the capacity of the FPGA. So that means you can swap in different functions when it's runtime. Yeah, so it kind of increase the capacity of the FPGA device. And another advantage is a standard CMOS process. So that means the FPGA and other CMOS functions, they can integrate into one die. Okay, so it gives you higher integrations. So increase the integrations and higher speed and no dynamic powers. That's the advantage of CMOS process. But disadvantage is using a 6 transistor SRAM cells, so the size is big. Yeah. Another disadvantage is the volatile. So that means once the power lost, then you lost all the function of the FPGA device. So you always need an external EEPROM. Okay, then when the system boot up, it can load the image, the bitstream file from the EEPROM. Okay, so like in the pink board, that you have a SD card, right? Yeah. When it's boot up, that the FPGA overlay will automatically load it from the SD card into the FPGA. Yeah. So this you need the actual external component, so it's also costly. Yeah. And it's more power. Yeah. So every time when it's power up, that you have to configure every time. Yeah. The current vendor like AMD, Xilinx, Intel, etc. Yeah. And it's actually the most popular way to do the FPGA programming. Yeah. Another technology is flash programming technology. Yeah. So all the flash memory using the floating gate. Yeah. So when you apply the programming voltage on it, they will trap the electron into the floating gate. Then you have a silicon. Then you will isolate, prevent the electron leak. Okay, so those are stuck in the floating gate. That's how it's programmed. So that's non-volatile. So these things doesn't need to power to keep its content. And you can reprogram like a SRAM, like a SRAM FPGA. Yeah, and so it's a very area efficient. It doesn't need 6 transistors. It just need one floating gate to keep 1 bit. And also you have a MLC and QLC. Okay, so that means for each floating gate, you keep 2 bits. QLC, you can keep 4 bits, 3 bits. So the way you have a different, using one floating gate to keep multi-bit is using the different voltage. That means a different amount of electron. Okay, so that's a, so you have a like a, if you want to keep 2 bits, then you need a 4 voltage states to keep 2 bit data. 3 bits, that means you have 8 states. So that means the electron can be just a few electron in there that make the bit difference. Yeah. For this MLC QLC memory, that it has a problem. It has only limited reprogramming. So that means it will wear out. Okay. For QLC, maybe you can like program few hundred times, maybe 300 times programming. Yeah. So that's why that it's hardly to reprogram every time. Yeah, doing the reprogramming. SRAM you can rewrite infinity times. Yeah, so there's no endurance issue for SRAM programming. For the FPGA floating gate programming, that you have because all the silicon floating gates will increase its leakage. Yeah, so that it cannot hold the electron to maintain its voltage. Yeah. Another big disadvantage is the non-standard CMOS process. Yeah. Okay, the vendor like a micro semi. Yeah. But it's cheaper. Yeah, because the size is smaller. It's a non-volatile. Yeah. Another programming technique is anti-fuse. Okay, anti-fuse means it's a reverse of a fuse. Okay, for standard fuse, that you have a fuse and then you apply voltage to break them. Okay, and anti-fuse, that means you apply voltage to connect them. Yeah, and the anti-fuse, that's the most area efficient. Yeah, so the area is small, and its resistance capacitance is small. It's also non-volatile. But the problem with is it cannot reprogramming, and it is not the standard CMOS process. Yeah, and it has a vendor, but this one is good for embedded use, for program once use, like a certain ID or a device. Once it's programmed, that it just use, and there's no need to reprogram. So this anti-fuse FPGA use in very small capacity embedded use. Yeah. So this is the comparison with among the SRAM flash anti-fuse FPGA. In here, we will pay attention to the density. Okay, density. This one anti-fuse most higher density, and this one is less dense. Yeah, and reprogrammable. Yeah, the SRAM is reprogrammable. Yeah. So actually, this one SRAM, yeah, is the most popular use. Although the size is bigger, but it can do the in-field updates. Yeah, so another reason that people use this SRAM-based FPGA, and that's the largest market. Yeah, in the FPGA market. Yeah. Okay, in here I would like to talk about in particular Xilinx FPGA architecture, because we teach the Xilinx FPGA, and it has the application specific modular block. Okay, so the idea is each function is arranged in a column base. Okay, so like this one. Okay, so for each column, it can have a different function. In this, for example, in this one, it has mostly populated with the memory. This one is the memory, and the logic, and the DSP. Okay, so this one application is mainly for computation. You can see, yeah. And then for this one, you see you have mostly a hardware IP. Yeah. So this one may be the prefabricate, like the SoC kind of application. Yeah. For this one, you see you can have a mixed signal. Yeah. So this one may be like Xilinx has a RF SoC. So the SoC has the RF modules embedded in the FPGA. So with this column base for each column that you embed different function inside, so you can target different market application. Yeah, and depends on the it's very scalable. Yeah, depends on the cost you need. So this one give you a more in-depth see how all the resource embedded in the FPGA, and it has a so-called large region. Okay, and for each large region, that's the column base. So you can see that they can put the I/O clock, yeah, and transceiver mixed with the computation component, which is the CLB, DSP, and memory block. Okay, and furthermore, it partitioned into the clock region. The clock region is for the power and global signal wiring. Yeah, and this is a region of inside the clock region that it has a combination, a mix of the CLB, DSP, and block RAM. Yeah. So the amount of DSP or CLB it's been architecturally fine-tuned so that with this resource arrangement, it can optimize for most of applications. Yeah. So you can have a 2 DSP slice with 5 CLB and 1 36K block RAM and aggregate and put together as a 1 DSP tile. Okay, so you probably need to have an idea how it's arranged and how much resource in it. Yeah. So when you remember when you're doing the high-level synthesis, if you look at the resource report, you will see how many LUT used. You see how many DSP, how many memory block. Okay, and those things has a certain ratio in the FPGA. Okay, and there's another concept is the memory and computation. Actually, these two things is that can exchange. Okay, I don't know whether you know this concept. Memory actually is a kind of a computation. For example, that for example, for certain computation, if that's the fix, you can compute the result offline and pull the result into the memory as a lookup table. For example, sine, cosine. the computation. Instead of you are doing Fourier transform, yeah, you actually put the lookup table, right? And then you do the scaling to get the sine cosine computation, right? Yeah. So basically, you trade off the memory with computation. That's one example. Another example is the compression. Okay. A lot of design techniques actually leverage on this concept, like a compression. Yeah. Let's say that the FPGA, you have a limited memory capacity, for example. Okay. For example, use the memory to save the weight of a neural network. Okay. If that's a big network, then you have a lot of parameters, weight, and it could not be saved in the on-chip memory. If you cannot save in the on-chip memory, you have to get the parameter from the external memory. There will be power consumption is very high, latency is high. Okay, so you really want to save the weight in the on-chip memory. However, the weight is so big, the capacity of the weight is so big, could not save in the memory. So one technique is to compress the parameter, compress the weight, so that you fit into the memory. So when you want to do the computation, you have to get out, read the data from memory, and do the decompression, right? Okay. So you use the computation to trade off memory. Okay, that's another example why I say memory and computation is two view of one thing. Yeah, and there are many other examples that you do this kind of transformation, memory and computation. Yeah. So that's here. Right now, FPGA, you have a fixed ratio among CLB and background. Okay, so how you can fit your design into this structure? Yeah, so that's why I mentioned this concept, memory and computation trade-off. If you use up a lot of CLB computation, so maybe the background is there, it's not used, it's not balanced because it's there, yeah, occupy the area. So why not you use the background? Yeah, then you may trade off the memory with the computation. Yeah. Okay. So with the Xilinx, the architectures that before we only put the I/O on the peripheral. Okay, that the disadvantage is the I/O and the array size cannot be independently scaled. Oftentimes, if this application involves a lot of I/O, so but not much computation or memory needed, so creates so-called I/O bump. Okay, so remember I/O is increased linearly, but the die size of the computation is increased square. Okay, so it's not balanced. Yeah, you pay a lot of price to increase your I/O. Right. So for Xilinx, they can put the I/O in the middle of the die. Okay, so it won't limit by so-called I/O bound issues. Yeah. And another good thing is before all the I/O power is supplied through the peripheral package. At that time, it's a wire bound because that's the technology advance. Yeah. Before it's a wire bound. So wire bound, you wire from the peripheral to the bounding pad of the package. But right now, it's a flip chip. so that the power can go through the bump and solder on the substrate. Yeah, so that's basically the package advance. Yeah. So with this arrangement, the power doesn't need to go long way to the center of the die. Yeah, you can inject the power in the middle of the die. Yeah, so that reduces the power drop, increase the speed. Another advantage is the if you want to increase uh, the area size, yeah, can be constant, yeah, as a feature scale. If you feature the area for your functions increase, then you increase the die size, yeah. And right now you can just popular with a different ratio of these features, yeah, and maintain the same die size, yeah. So it gives a lot of benefits. So that's why these architecture invented many years, and they still use the same architecture, yeah, till now. Yeah. Another thing, you want to increase the capacity of the FPGA. Instead of have a larger die size, you actually put multiple die on the substrate, and you use so-called SSI technology to interconnect different dies. The SSI stands for Stack Silicon Interconnect. So this is one die. That's another die. And then you have a routing channel between them. And the routing channel was wired through interposer. So this is the so-called interposer. The interposer actually is a fab process, so it is a wafer. So those die are on the wafer, and they are wiring through the interposer. So this is the semiconductor process. This is the semiconductor process. So it can have a very dense wiring between them. Yeah. And then the whole thing, the interposer will pull on the standard package substrate. And then you have a FPGA bump pull on the PCB. That's how you stack the die. Yeah. So with this kind of package we call 2.5D package. Yeah, it's different from the actual 3D. The actual 3D package we call TSV, through silicon via, and this one, yeah, using an interposer instead. So that's how you see that the SLR in the FPGA. You may have a depend on the capacitor. So that's why Xilinx can fabricate one die but offer different device. If you look at the Xilinx device table, you will see they offer all different devices. So the difference is they simply stack different number of FPGA die to give you different capacities. Yeah. So you will see a FPGA like a U50. I don't know how many SLR inside. Yeah, maybe two. Yeah, for bigger capacity may have a 4 SLR. Okay, so that means it's 4. But this, so when you are doing the design and you try to group the logic inside one SLR, one die. If your logic has to across two die, this one, although has many connections, maybe 10K connections, but the delay is still big. You slow down your function. Yeah. So it's not totally transparent. Yeah. So you have to have a knowledge about the SLR, each die, that so that you can do good planning on your logic. Yeah. You can specify certain logic for on certain die. Yeah. So that your speed won't be downgraded. Okay, so this is a question that what's the benefit of SRAM-based programming? Yeah. So anyone want to answer? Hmm? So first, you can do the in-field programming. Yeah, that's right. Yeah, the size is smaller compared to the other two. We know the CMOS process, right? It is a number type. No. Okay. Yeah, I think the most key advantage is the CMOS process. The other, like a flash or anti-fuse, they are not CMOS process, so they could not do the integration with other functions. Okay, let's talk about the CLB, configurable logic block. Yeah. So this CLB actually is only half of them. Yeah, one CLB for ultra scale. That's the FPGA you use today has a ALUT, and here I only show four of them. This is a four LUT. So you have a four LUT. That's provide a 6 input lookup table. Okay, 6 input. That means for each LUT you have 64 bits as well inside, right? Okay, and then you will see there is for the LUT you have a lot of marks. Okay, yeah. So if a marks connect these two and connect these two and the marks connect these two, yeah. So you have a wider marks, and each CLB, each LUT can be used with as a distributed RAM. Yeah, as I said, the CLB actually made up an LUT made up of 64-bit SRAM. So this SRAM can be used as a memory. They call distributed memory. And this LUT, the memory can be used shift register. Yeah, and shift register is used a lot. Yeah, very popular in many of the applications. Yeah, and you have a carry logic. This is the carry logic. Yeah, yeah. And you also have those are the flip flop. Okay, so this flip flop can be used as a latch and can be used for the storage. Yeah. So that's the content of a CLB. So let's look at its resource. Yeah. Again, only show half of the CLB. Okay. So for each CLB, you can have 8 LUT. And for each LUT, you have 2 flip-flop. So you can have 16 flip-flop. Yeah. And you can have a 8-bit carry chain. So this carry chain can be used for the adder. Okay, for certain arithmetic functions. Yeah. And you have a wider marks. You have those marks. And those, we use the marks to implement logic function too. Yeah, and I will explain that later. Okay, so an LUT lookup table. So the CLB can be configured using its logic function. That means the LUT is used as a logic function. Or you configure the LUT used as a distributed memory. So it becomes a slice M. Okay. So so for a slice M, since for each one is 64-bit and you have 8 LUT, so you can have 512 bits memory. Yeah. Okay. So as a storage, an LUT can be used lookup table. You can use a 64-bit distributed RAM or 32-bit shift register. Okay. So that's a CLB resource. Okay, so the LUT, one slice has 8 LUT and 16 flip-flops. So for LUT, you can configure as a 6 input, 1 output lookup table, or you can use 5 input, okay, 5 input, 2 output lookup table. Yeah, and for each LUT, you have 2 flip-flop to use. Yeah. So this is a LUT function. Yeah. You program the SRAM, and then you form the different logic functions. So this is a LUT. Okay, this very interesting things that for the neural network, okay, you have a sum of a product and a batch normalization and doing the threshold activation. So you can aggregate them. Then it actually becomes a 6 input and 1 output. Yeah. So this as long as you can make, of course, that's a binary neural network. Okay. So you can actually aggregate the sum of a product here, the batch known and activation. So aggregate is a 6 input and 1 output. So when you are doing the neural network training and with quantization, and later on you can map into the LUT. So it's a very, very efficient, yeah, in terms of area. And that's a paper, this is an open source. You can use, that's using in Fin, because the Fin is based on the BNN. Yeah. But if you use a lookup table to implement this neural network, you know that if you have a neural network, you have an X input and Y output, how many bits you need? How many SRAM bits? So that's a Y times 2 to the power X. So along with the number of input, that's exponentially increase, right? So imagine that if I have access 10 bit from 6 bit to 10 bit, you increase 16 times to the power 10 versus to the power 6, right? Yeah. So that's why to use this one, you need a special training and quantization techniques, so that, for example, you have a very extreme pruning, yeah, or you take advantage of sparsity of the neural network and partition it away. So you need very sophisticated compiler to make the neural network from training to the LUT. Yeah. But once you do that, it can run very efficient. Yeah. So people invent this. They want to do 100 million inference per second. So no way you can have any NN accelerator can do this extreme throughput. Yeah, but with LUT you can do that. Remember, each LUT, if you run at the 300 megahertz, yeah. So yeah, then 100 LUT. So it's feasible to throughput. So why people use what kind of application that needs that much inference? For example, the network, the intruder detection. Okay, remember, imagine if you're 100 gigabit Ethernet or 400 gigabit Ethernet. And for each packet comes in, then you have to look up the packet format, the pattern, to find out if this packet is falling into any of the virus packet format. Okay, so you need run very, very high speed to do the inference, to do the in-packet, real-time in-packet detection. Yeah, so that's one example why you want that much throughput. Yeah, there are other applications too. Yeah. So that's if you're interested, you can refer this. So that's the one use for the LUT. Yeah. Okay. So also that can form a wide max. So for 6 input, 1 output, you can do 4 to 1 max. Right? 4 to 1 max is a 3 input. Yeah. So you can form the max. And then put 2 LUT with a max. That's all in the CLB. This max also in the CLB. So you can have 8 with a 2 LUT, then you can have a 8 to 1 max. Yeah. And you put 4 LUT, you can have a 16. Basically, you can have a, 4 LUT, and then, you can have a 16 to 1 max. And for one CLB, you have a 8 LUT, so you can have a 30 to 1 max. Yeah. And furthermore, that this is one CLB. Okay, that's the interconnection, inside the CLB. And you can observe that you have a total 6 times 8, 48 input here. Okay, and you have each max, you have a select here. So you have a total 7 select. So you can form 55 input Y function. Yeah, you can use one CLB, you can form a Y 55 input function. Yeah, so it's quite powerful. Yeah. Okay, let's talk about CLB used for storage element. So besides the LUT table, okay, that give you one LUT give you 64 bit, and one CLB give you 5 12-bit storage. And you also have a flip-flop. You have a 16 flip-flop, and it can also be used latch. Yeah. And for this flip-flop, you can take different input sources. And one you can directly use for direct input. Yeah. So that means the flip-flop can be used independently. Yeah. So the input is not necessarily from the LUT, can be directly for external connections. Another advantage is that provide 2 sets of a clock. Yeah. So that means this flip-flop can across different clock domain. So that's the clock A and clock B. So you can do a clock domain synchronizer. Yeah. Okay, inside you can do the fast carrier lookup logic. Yeah. So basically, you can connect them to form a wider adder or subtractor logic. Yeah. Remember, we have a DSP, right? Sometimes you have a small bit adder or subtractor, so don't use a DSP. It will be too waste. Yeah, you can use the CLB to do the simple, arithmetic function. So LUT as a distributed RAM, yeah, and you can use as a 6 input, 1 output. That means you have a 64 bit, yeah. So or you can use if you use a 2 output, then becomes a 32 by 2 distributed RAM, yeah. Okay. So for one CLB, you have a total 512 bits. So how do you configure to use the 512 bits? Yeah. So basically, you can form different number of ports. Okay. And then you can have a different depth and different bit width. As long as this altogether will be less than equal 512 bit. So you can do all kind of configuration. For port, you can have from one port, single port, to quad port, to 8 port. Yeah. For depth, you can maximum to 512 times 1 bit. Yeah. For bit width, maximum you can up to 16 bit. That's reasonable because each LUT can give you 2 output and you have 8 LUT. So maximum give you 16 bits. Yeah. So given this range, then you can form all different kinds of configuration of the distributed RAM. As long as they all put together less than 512 bits. So it's very flexible. So this distributed RAM can be used as a shift register. Okay, imagine. So maximum the shift register is 256 bits. Yeah, it's half of 512. Yeah, why is a half? Remember, SRAM you can think of as a latch, right? You can have a latch. To form a flip-flop, use a two latch and make the as there's a clock, master slave. That's how you form a flip-flop. Yeah, and you one flip-flop you can do the shift function. Right. So total you have 512 latches for SRAM bit, and you form 256 half of the register. Shift register. That's a shift register. Yeah. Okay. And shift register is very critical, often used in many of the applications. Yeah. Remember the FPGA is good for data flow architecture, right? Data flow. Yeah. So for data flow architecture, you have that's a text pipeline. And interface between them, you use a FIFO, right? Okay, so the FIFO is a shift register, right? So it's also use a latency, bridge the latency. Yeah, let's say that you have a data flow. Okay, there's a task one. Okay, take this much latency. And you have a task two, another task. Okay, And these two tasks will be merged into the third task, right? Okay. And since they have assumed this tool has the same throughput, let's say that it can do II equal 1. That means every cycle it can produce an output. So test 1 can generate one output. Test 2 can generate, every cycle generate one output. But test 1 and 2 has a different latency. Yeah. So in this case, you need shift register here. Because this one, to bridge up the latency, that's what I'm saying is for latency compensation. Yeah. So that's another example why in data flow architecture design, you use a lot of shift register. Yeah, because each task has a different latency. You use a shift register. And can be use a FIFO. And also use a content adjustable memory CAM. Okay, CAM is a very common data structure used in many applications like Ethernet routing, right? So for every packet comes in, you look at the header, then you find out the source and destination address. You look up, and then you find out the link status. So you do a lot of content addressable. Use a lot of CAM, yeah, in Ethernet application. And many for searching, a lot of searching algorithm using CAM too, yeah. So that's why shift register has been used widely in many applications. Okay, let's skip the question. Yeah. So next, let's talk about DSP. Yeah. Now remember this architecture that you have a fixed ratio among the block run, CLB, and DSP. And one DSP tile has two DSP slices. Yeah. So this is one DSP slice. This one slice. Yeah. So for within one DSP slice, you have 27 by 18. That's the ultra scale FPGA. They provide this 27 by 18. And for one tile has two slices. So you can combine them to form 54 by 36 multiplier. Yeah. And with this multiplier, you have a pre-adder. Yeah. So basically, that's a MAC. There's a multiply here, and you have a 48 adder accumulator here. So each DSP 48E2, that means generation 2, that can provide that's a MAC, okay, 48-bit accumulator, yeah. And besides that, you have a pre-adder. Okay, the reason to provide pre-adder is oftentimes you have a filter, and filter you have a symmetric coefficient. If the coefficient is symmetric, then you can fold it. You can fold in them, yeah, so that you can reduce the number of multiplier. Yeah, if, for example, in here I didn't draw in here. That's your coefficient. Basically, that's a symmetric. That's symmetric. Symmetric. So doing the filtering, you can fold it. Yeah, fold it so you can add them together and do the. You add these two together and use one multiplication here. So you save the multiplier. Yeah. So that's the purpose of using a pre-adder here. Okay. And also, this one has a pattern detector, and it's very often used in many applications. Okay, so that's basically the structure of a DSP. Yeah. To use the DSP, there are a few guidelines. Yeah. And those guidelines you may not be aware, but however, for certain applications, if you want to manually manipulate the use of DSP, then you can consider this usage guideline. Yeah. And so the DSP can be doing the pipeline. So there's the option when running different speed, you can have a different pipeline because the multiplier has a pipeline stage. That so if you run a higher speed, then you can add a pipeline. And often, as I said, so for doing the filter or doing neural network, you need a lot of parameters, like a coefficient parameters. And it's better to use the, because the parameter is a small amount of data. Yeah. So it's better to use the CLB distributed memory. Okay. Remember the CLB and DSP, they are all nearby and very close. Yeah. So instead of using the block RAM, because the size is 36K bits, that's too big, and CLB 16, you have a 64 bits. So one slice CLB is 512 bits. So it's good for storing the coefficient. Okay. So it suggests using a CLB distributed memory to save the coefficient instead of using block RAM. Yeah. And also the DSP tile, they can cascade. Yeah. And when they cascade, the interconnection is a pre-wire. So it doesn't use a wiring resource, doesn't use an interconnect wire. Yeah. So it's run a higher speed and save the resource. Another thing is if you have a lower speed application, many applications that the throughput rate is not high. So you can use a time multiplex of a resource, yeah, to use the DSP. Yeah. So that means the DSP is used time multiplex. Okay, you can save the use of a DSP. And mux, remember CLB has a lot of mux inside. Yeah. And if you are doing a small bit width of a arithmetic adder or counter, it's better using a CLB carry logic instead of using a DSP. Yeah. Because a DSP is the resource is limited, not as much as a CLB. Yeah. Okay. So to use this specific application, you can manually control the HLS compiler using these two programs. Yeah. So this is the type of application, yeah, very common used in signal processing, using telecommunication, video, image, yeah. So DSP is used everywhere, yeah. So that's one example. You can refer this white paper that tells you how to use the DSP for doing the machine learning. Yeah, that's a very good example. So basically use a systolic array and each of the element is made of DSP. Okay. And to use that, we know that for neural network operation that you need many data source coming from, okay? Then you really need a lot of memory bandwidth, okay? So for one CLB, you can provide like up to 10 port. Like you have a 8 ALT table, right? Yeah, for each one, yeah, they provide a different memory port for you. Yeah. So it's good because you need a lot of weight and then used by different operations. Yeah, so you need a very high memory bandwidth, and the CLB LUT distributed memory give you a lot of memory bandwidth. Yeah, so you can reference this paper. Yeah, if you want to use DSP for doing the machine learning. Okay, so let's talk about RAM. Okay, so inside the FPGA, you have using CLB as a distributed run and use the flip-flop. Another one is a block run and ultra run and high bandwidth memory. This is a block run. So basically the block run, each block run gives you 36K, and then you can use half of them separately. Okay, so when use HLS synthesis, it reports the block run usage is actually used as a unit of 18K. Yeah, because half of the block run can be used independently. Yeah, and if a block run need to be initialized, okay, so actually the initialization is done in the bit stream. So when the system boot up, you load the bit stream, you also initialize the content of the block memory. Yeah. And for timing, you have a output register, and it can have a independent rewrite port. Okay, and in here, you need to know so-called the simple dual port, and true dual port. Okay, for simple dual port, that you can have only one data port, but rewrite independent, but with one set of data port, data input and data output. That's so-called simple dual port. Okay, dual port means rewrite. But for true dual port, that's a true dual port. So you can imagine that's a totally independent. You have a separate write port, not just separate write port and read port, and you have a different data output. So that means that these two ports, you okay, because you have two data output, you can use the two write. You have a two data input assets. Yeah, and independent or rewrite. Yeah, in here you cannot have a two read, two write. You can have only one write, one read, and each one data port. So when used as a true dual port, your bit width reduced. Yeah, simple dual port you can have a 64-bit. A true dual port only 32-bit data. Okay, so there's a block run. And you can have an option output register for timing sake. And you can increase the block run size by cascading block run. When you cascade, for example, you can put 4 block run. So you increase the capacity. And this is the final output. So depending on the address, the data coming from different block run. So for the data, you need to cascade them to output. So you have to go to many level of max. Yeah. So you can have an option, but the tool will automatically synthesis using register output. For example, you can go here, have a register, repipe the timing. So it saves the timing. Yeah. Or you can have a last stage, goes to the register output. Yeah. So you can cascade them, and depends on timing, they will insert the pipeline register. Okay, since the block run for the reliability consideration, you can have a ECC. ECC, that means you will have a parity generation. That's the ECC encoder. And when you read the data output, then you have error detection and correction. Yeah. And those logic are built into the block run. It does not use the CLB resource. And the block run can be used as a FIFO. Okay, the FIFO, so it has built-in the right pointer logic, a read pointer logic. Okay. And besides that, this FIFO, you can have a different write clock and different different read clock. So this FIFO can use as a bridge of two different clock domains. So it can be used asynchronously, yeah, to bridge two different clock domains. Yeah, the FIFO like a block run, yeah, you can cascade them. Yeah, and let's talk about ultra run. Yeah, ultra run is much efficient use the die area. It provides larger capacity of the memory. It actually aggregate the capacity is 8 times the block run size. Yeah, and it can only offer as a single dual port. Okay, and you can cascade the ultra block run. The ultra block run can maximum depends on the capacity of the FPGA. Maximum it can up to 300 megabit. The way you cascade them, you do a two-dimensional array, and with some pre-wire address decode. Okay, so you can cascade ultra RAM to be a very big memory. Okay, HBM. Okay, HBM stands for high bandwidth memory. This chart tells you that in the 10 years span, the Ethernet bandwidth from 10 gigabit up to proposed 800 gigabit. So that's 80 times bandwidth increase. And for video from 2K to 8K, you can see 8K TV, yeah. So that's a 4x increase. For DSP, has a 2,000 slides increased to 12,000 slice. So you increase 6 times. However, if you look at the memory, if from DDR3 to DDR4, the bandwidth only increased 2x. Yeah, so you know there's a big gap between all different interfaces. Yeah. So that's you need a very high bandwidth memory. To do the high bandwidth memory, you there are two ways to do that. One is you try to stack the memory, and like the SLR, silicon interconnect. Yeah. So you put the memory die and FPGA die side by side, and using the interposer to connect them together. And this technology called CoWoS. That means chip on wafer. This chip is on wafer. Interposer is a wafer, and the wafer on the substrate. Yeah, that's a chip on wafer on substrate. Yeah. So doing that, you can have a very dense the connection, the bump. Okay, it's very dense. So I/O area only 20 times less I/O pad size. Yeah, and the reason is small because the single it's a process technology, so it's a much less capacity loading. So the driver size is small. Yeah, so you don't need big drivers, so you reduce the size. So by doing that, I/O connection is in the middle of the die, so you can have very high bandwidth in the connection. So you look at the bandwidth comparison. So for today's DDR4, you can achieve around 20 gigabytes. And for HBM, you can have 400. So it's about 20 times more bandwidth. And what is promising is look at the power consumption. To transfer a bit, for DDR4, it takes 27 picojoule, and for HBM, only 7. So for this, you have like 4 times reduced in terms of the power. Yeah. So you get a much higher bandwidth and less power consumption. Yeah. And there are two kinds of connection. One is that's I call 2.5D package, and that's a true 3D package, and the on top of each other and through the TSV connector. Yeah, so you can see you can stack them, but not infinity. I can pull 64 of them, like a flash memory. Yeah, a year or two ago, Samsung announced their flash flash chip. Yeah, so that's why the capacity increased a lot and using the TSV. Okay, so you can put. So for HBM application, that's basically any application that need bigger memory bandwidth, then you can use HBM, like machine learning. Yeah, the security plans and mostly use larger lookup, so you need very high bandwidth. And also it can be use level 4 cache, yeah, bridge to the DDR memory. Yeah. Since the HBM provides such high bandwidth, and remember the HBM, the memory may run as a, for example, 3.2 gigahertz, and you have 1,000 interconnection then, and you have a multiple die, right? Yeah, but inside the FPGA, it could not run at that much speed, maybe only 300 megahertz. Okay, so how do you consume that much bandwidth? That means that you need a lot of signal, right? Yeah, because the speed running slow, at least 10 times the signal, right? So that's why you see very weird. Yeah, and you cannot lay out all the I/O in flat line. Yeah, because there will be too many I/O. Yeah, so that's why you lay out in this way. Yeah, you need peripherals. Yeah, yeah, to pull all the I/O interface. Yeah. So also in the FPGA, the U50 using the HBM. So in system application, you can have a 32 memory channel. And each magnet channel, you can have a 256 data width in order to fully utilize the memory bandwidth provided. Yeah. Okay. Okay. So we will finish the class soon. Yeah. So let's talk about the routing. Okay. Okay. Very important concept is in FPGA, routing resource is the most critical one. Most critical one. Look at this number. The routing network takes up 80 to 90% of the area. It's used for routing. Yeah. And also the memory bit, 98% of memory bit not used to store data, used for the interconnect connection. Yeah. And so limited that you have to design your architecture to fit into connection, fit into the connection resource. If you run out the resource, the CLB goes unused. Okay, imagine you design something that using, let's say you have a 32 by 1 max. All 32 data coming from different sources and coming out one output. So that means that all the wiring has to go into one place. So it run out the interconnect resource. So it's better design in a way you distributed the marks. Okay, so maybe you have a 16 marks, and then you have 8 of them, and then 4 of them, and then final one. Okay, so you like to have a structure like this one. Yeah, so that this one you create congestion, run out the interconnection resource, and this one you even out the interconnections. Yeah, and this one also favor data flow architecture. If you have a function that has a lot of sharing, yeah. For example, you have a one variable, cache memory, for example. This data going to share by many operations. Okay, a lot of processing element, for example. All the processing element going to use the same data. If a architecture design this way. So with this way, you better design that you have the data actually fall through by the processing element to another process element. So this common sharing resource only goes one place and use the PE because they are geographically diverse, okay, in different locations, right? So that even out the interconnect resource. Okay, so you don't pull everything, yeah, congested. Yeah. So maybe you design the systolic array or data flow architecture that also use the processing element to propagate the data. Yeah. So that's another area in architecture design. Yeah. So you can design something very simple-minded. Yeah. And then you share common resource. But the problem when you do the physical implementation, and it says it cannot complete. Yeah. So in this case, that you have to re-architect the whole architecture by consideration the interconnection resource limitation. Yeah. Okay. So probably I don't go through all those details. Yeah. Yeah. So there are two types of interconnection. One is a connection box, one is a switch box. And for the connection, they define different parameters. For the switch box, there's a parameter FS3. That means for each incoming, you can connect to three other connections. And that's a connection box that for each pin, you can connect to three wires. Yeah, three channels. Yeah. So all takes up the resource. Yeah. Okay, so probably I don't go through. So when the design the FPGA architecture, it needs very detailed planning on the wiring resource. So in Xilinx FPGA, it has a different length of a wire. It could have a wire extend only locally, okay, or across the 2 CLB or 4 CLB or a global wire. Yeah. So how many resources to allocate for each type of wire? That's a secret sauce of the FPGA. So when they architect, they run also the verification and then doing a very detailed analysis and finally decide this configuration. Yeah. Even though with this so-called optimized interconnection, that's very easy to run out interconnect resource. Yeah. Okay, so this is the interconnect. So in here, you just remember interconnect is a very precious resource. Yeah. So you need to design architecture accordingly. Yeah. Okay, this one we already talked about the die interconnect. Yeah, this one also. So yeah, that's all covered. Yeah. So that's the way you read the device table. Yeah, you need to watch out for the how many CLB and CLUT. Yeah. And there's a distributed RAM and how much is the block RAM and ultra RAM you can use. Yeah. So that's mainly you look at this, and then as I said, this FPGA just have a different number of die package on the wafers. Yeah. Okay, so I think probably this less. Yeah. FPGA resource binding. Yeah, using bind up. Yeah. So probably I don't go through the detail. Yeah. In the future, I believe there's a lecture on this one. Okay. So finally, we finish this talk. Today, I still don't have a chance to talk about the from gate to HLS. Yeah. Probably this semester, I won't have a chance to talk about that. But for that gate to HLS, basically give you an overview on the logic design, from combination logic to sequential logic, yeah, to value coding. Yeah, just quick go to. But I believe you may have a logic design background. Yeah, maybe. Yeah. Okay. So this concludes today's